everybody, for coming. I'm pretty sure there was a fair few more people here for the test, but never mind. Yeah. So, hopefully a lot of you people recognize me from last year. I'm the lecturer who looks about 14 years old and who sets hard exam questions. Yes. My name's David Boland. I taught a lot of you 272 last year, and yes, so I'll be taking the second half of this course. Now, this is going to cover mainly the real-time aspects, real-time operating systems, and frankly, it's probably the more interesting part of the course. More interesting also probably means harder, so be ready for that. So first off, pointing off, I'm going to make use of this website, which just has all of the lecture notes, the laboratories. You'll go off it. There's a link off Moodle, so you can use that when ready. It's worth having a look at the resources it has listed on here, just in case you don't realize. Monash has a relationship with Microsoft, so all students can download Visual Studio if they need to. We've got lots of code examples we'll be walking through in these lectures. If you really want to learn it yourself, the best way to do it is just to download the code yourself, run it yourself, hack around with it, and that will be the best way to prepare you for the exams as well. Speaking of the labs, again, the labs, I think you'll find that both of these two labs, they are scheduled for 2 weeks, but they are actually an awful lot harder than the labs that you've done, labs 1 to 5 so far. So be willing to put some time in beforehand and just accept that that's the way. Previously, there's been some complaints that there's not enough marks allocated to these labs, but the thought process is A, you've got the lab test, so you're getting marked on it there as well, and B, once again, by doing the labs, you're going to learn all the stuff which will make the final exam a lot easier. So, just general advice. So today, we're going to be talking about processes and a bit about operating systems. Now, I've deliberately made today a bit light, mainly because I know you just had the mid-semester test. You may well have other mid-semester tests, so I didn't want to push it too much. So we're just going to introduce processes, why we use processes, and then mainly get on to talking about multitasking. What are the different methods for multitasking? Why do we need to do it in the first place? Context switching here is the key process within multitasking. It's saying, stop doing one process, do the next process. How do you do that switch? Okay. I want the lectures to be interactive if possible, and so I've prepared a practice question for you all. Yay, and I want lots of participation, please. So, because, again, you just had your mid-semester test, I thought I'd make it a completely unrelated practice question, and it's to do with football. So, first up, when I said football, who thinks I'm talking about AFL? Leave the room. There's only one football. That's what you people call soccer. Okay, the key question that is going to be asked is, should a penalty be awarded in this instance? So, this is the instance. Now, this is a staff student soccer game. Now, obviously, you'll notice the staff hired Cristiano Ronaldo. But of course, the star player here is lying on the floor appealing to the referee. Now, before you make your decisions on whether a penalty should be awarded, you should be aware here, you might be able to see, but maybe not, there is a white line there. That's the box, so you can see the foul occurred within the box. You may want to look at the guilty look on that person's face, and the look of disbelief on this guy's face in the background about what is going on. So, hands up who thinks a penalty should be awarded. You guys are as bad as the rest. Right. So, back to the real stuff. So we're going to be talking about processes, abstraction, multitasking, yada yada. Okay. So, process is a unique execution of an independent activity. So, the key, these two lines, unique and independent, the point which they're trying to highlight here is if we're thinking about a bit of code, we can have multiple executions of the same code. Each execution will be a separate process. So they're independent activities because they're running separately, but we can use the same code. And this is what's highlighted here. Of course, here it says several copies of a program may run simultaneously or at different times. So, how do you run several copies of a program simultaneously? Any suggestions? Sorry? Think. Well, what do we need to run a program? We need a CPU. How do we run multiple programs? Simple. Yeah. Or with hardware or something. Of course, in this topic, we're going to be focusing on single-core CPU. How do we share all the tasks throughout this process? Every process has its own state. So this means it has registers and memory. So the registers are what it's performing all its local tasks on, and it has a special space in memory which you shouldn't be able to access. Only an individual process can access. This is important because as the process leaves the CPU, it has to store its current state on memory somewhere, and at some point it's going to have to look at this state in memory, retrieve those values back into its registers and continue processing. And generally speaking, though not necessarily, the operating system is the thing that manages the processes. So why do we have multiple processes? The idea is it helps us manage timing complexity. So the idea is that we can have lots of processes, each thing has multiple rates, and we can have asynchronous inputs, which may stop a process, cause a new one to start. Now, I thought this sounds a bit wordy, and I think it's best to show it an example. And again, light example, we're going for a completely unrelated my life example. Now, last weekend, my wife had dinner with her girlfriends, or at least that is what she told me. She went to have dinner. Right, so these were my tasks for the evening. I had to cook my own dinner, I had to eat my own dinner, and then I could chill out and watch TV. Now, as you can see, this is a very simple thing. I've got three processes, process 1, process 2, process 3. And if I want to plan this evening, I fortunately can do process 1, process 2, process 3. It's not difficult at all. So I don't need any fancy processes. I don't need operating systems. I can just run this in a single bit of code if I was me being a computer running these tasks. We have new tasks, and these new tasks have different rates. So yes, I have process 1, 2, 3, which has to happen once a day. But now I have to play with my baby, and otherwise he screams at me. So I have to do this maybe, every half an hour. I have to clean up his toys, otherwise I start tripping up on them. This will be every, hour. I have to feed him. It's pretty straightforward. This is a recurring task throughout dinner, so that might be every 2 minutes. And then I have this task here, which is an asynchronous task, which I hope I do not have to perform until my wife gets back home. Right. So, suppose I wanted to schedule my evening and plan it, and I wanted to write a single bit of code to do this. You can imagine that this is actually quite difficult. So this is, without processes, I'm trying to write a single plan for the evening and make sure nothing goes wrong. So first up, I'm making my dinner, peeling, chopping my onions, my garlic, getting ready. But I have to constantly check, is there a dirty nappy? No, I can, if there is, I got to change it, otherwise I can continue cooking, check the nappy again. Then I have to check, regularly, well, is he screaming? Okay, he's screaming, got to play with him. And then, yeah, if I left things, I got my burning food, I've got to turn off my stove. And so imagine writing this as a single bit of sequential code. It's near impossible to do. Whereas if you separate it into separate tasks or processes, you can make it very simple. I've got my cooking dinner, I've got my nappy. This can be an asynchronous thing, which my operating system says, okay, you've got to do it now. Similarly with this guy. And these tasks, well, you might say that this one's high priority, this one's low priority. But you can imagine we first feed the baby, then while he's chewing, then I might start to feed myself, and then so on and so forth. So you can see how an operating system, I can define my tasks very simply, and I can let someone else do all the work of what order do I do it. More formally, so this is because I should be sticking to a textbook, not just giving my own life examples. This is from the textbook, kind of same idea. Textbook is here, by the way, if you haven't seen it. So if I have some form of engine controller, the idea is the engine, the only task it really has to do is set this spark plug going. Send a spark, which ignites some petrol, and that gets this crankshaft spinning around. Now, you can imagine that the key in this process is you got to ignite the petrol at the right time, otherwise this crankshaft might be going back and forth if you didn't time it correctly. So what you have is you'll have some kind of sensor here which regularly checks where this crankshaft is currently located. That will feed back into when I do send up my sparks. I'll have to check fuel-air mixture, so I have to check this if he pushes the driver pushes the petrol down, the accelerator down, you need to change this. Your oxygen, you need to constantly measure. Say if you go above sea level, your oxygen level changes, that will change the result of the ignition, so you need to change your fuel-air mixture. So you need to keep a track of this. You might have some more complex processes running within the engine controller, so you might have a common filter. This is something that tries to get a steady reading out of random variables. So what is the real state of my system given that there's some noise in my measurements? And you might have some state machine doing some other processes, checking if you turned on the lights. And this is all held within a single engine controller. And once again, if it tries to write code in a single line without processes, it gets very complicated, especially when you consider that this A code will be a single process. So you'd say, I start running process, I'm going to stop running it, start running a bit of B. Scheduling all in that in advance begins ridiculously complicated. You get what results in so-called spaghetti code, which is code that is basically impossible to read, because if you follow the context, it starts to go down, then you split up, go to another variable, another function, and it looks like spaghetti. Okay, so how do we do multitasking? So we're going to talk about 4 main methods today. First is coroutines, then cooperative multitasking, preemptive context switching, and interrupts. Okay, so coroutine might be the earliest type of method to do context multitasking. And the idea is that you have multiple subroutines, and each subroutine says, okay, I want to do a bit of work, but then I'm going to give up control to the other subroutine. And the key about coroutines is that the pattern of control transfers is embedded in the code. So you have to say which routine is coming up next once I finish my current routine. which means that you really, if you're writing coroutines, you're actually going to be going into something like assembly code because you have to control all the registers and who gets the next control of the CPU. So this is an example of what some coroutine may look like. It's written in ARM assembly. Now, everything you've done in this course so far is NEOS. You should be comfortable guessing roughly what's going to happen in different assembly languages because they're not too different. And ARM is obviously a popular one. It's one of the largest chip companies, or growing chip companies now. It was originally based in the UK, and essentially grew an awful lot when Apple decided to put an awful lot of them in their iPods, iPads, etc. So, what does this code look like? So, imagine I have some kind of initialization. I'm going to say store this address here in register 14. Then, can anyone look at this code and roughly tell me what it does? Yeah, so this puts the address of code 2 into register 14. What does the rest of the code do? Well, perhaps what you might realize is that this code literally does nothing because there's no processing. So these dots you can consider to be doing some kind of work within a routine. Okay, so you start off here, you do some work within coroutine 1, and then you put my address of where I want to return to. I want to return, when I come back to coroutine 1, I want to return to call B. So I store that result in R13. Then I move R14 into R15. What does that do, anyone? Yeah, basically. So R15 is the program counter. So you move this address into the program counter. What that means is you go up to this point in the code. Now you'll run whatever function goes in coroutine 2, and then I will say, okay, when I get back to coroutine 2, I want to go to this point, so I store that value in R14, and then I load my program counter in R15 with what is stored in R13. What's stored in R13? It is, if you go all the way back here, it's call 1B. Now, of course, having looked at this, you know that in this code, you cannot use R13, basically. And similarly, in coroutine 1, you can't use R14. But yeah, so this is a simple way of controlling the execution. And I think, yeah. So run through coroutine 1, shift across to coroutine 2, run through coroutine 2, go back, continue, so on and so forth, and you'll get to the end. So that's coroutines. Cooperative multitasking is very similar, except you do the context switch by just saying CS switch. And so this CS switch call says, I've done the work that I want to do for now. I'm going to give my control back to the operating system and then let it choose what it wants to do next. Now note that you still rely on each processor giving up the CPU, and that's why it's cooperative. Okay, so what would an example code for cooperative multitasking look like? So note that now I've written something that looks a bit like C, and that's because we don't have to be so careful about doing the context switch ourselves, because the context switch is now done by the operating system. But once again, suppose I started with task 1, I'd do some work, I'd hit context switch, then I would say, okay, do some work here, hit context switch, do some work here, and so on and so forth. So it achieves the same goal. So, who thinks cooperative multitasking is better than coroutines? Who thinks the other way around? Coroutines beat cooperative multitasking? No one. So some people think this one's better, some people think coroutines are better. So generally speaking, yeah, cooperative multitasking is much better because you don't need to worry about all of the context switching yourself. You can have the code once written with the operating system. That is very carefully written code that's guaranteed to work. You're allowing less room for bugs. However, coroutines could actually run a bit faster because you don't have this overhead of calling the operating system. Let the operating system work out what to do next. So if you had an extremely simple system, then you might write a coroutine, but generally cooperative multitasking will beat it. However, that's not the more generally used. Perhaps better still is this preemptive multitasking. And this is the idea where the OS controls all the context switches, but the OS basically gets power more often. It no longer has to wait for a process to say, I'm done. It now waits on a timer. Now this timer might be every 1 millisecond or 10 milliseconds. So it lets a process do 1 millisecond work, 10 milliseconds work, and then it says, I'm taking over. And I'm checking if someone else needs to do some work. If another process is more important than you. Note that I've said here it uses a timer or other. Now, other could be a process. A process can still voluntarily go to sleep. It can finish what it's doing and say, I'm done, take back the CPU. Or it could be, any other suggestions? What could be another? Yeah, an external interrupt of any form. Right. Now, as you can see, if you now look at preemptive multitasking code, the big difference between this and previously is we no longer have this CS switch call within our work. We just write out our tasks, let the operating system take over and allocate which one is going to have the CPU at any given time. Right. So this is diagrammatically trying to show what's going on. So you initially have process 1 running on the CPU, and then you have this regular interval of an interrupt, and during this time the operating system is taking the call, taking over the CPU. At this point it says, okay, I've decided actually process 1 can still run, so process 1 runs again, interrupts again, goes, this time I decide P2 should come. So looking at this, can anyone suggest what is special about this second interrupt? Or rather, how come after the first interrupt, I decided P1 can keep going. After the second interrupt, I decided P2 should take over. P2 is higher priority. So if P2 is higher priority, why didn't P2 start here? Basically, yeah. So what's going to happen is P2 ran something here, and then it went to sleep. Or it waited for a resource. Then at some point here, it woke up. And it says, I'm ready. And what it does is then it goes to this queue on the operating system, says, look, I'm awake. But it can't run until it gets this interrupt, and then at this interrupt it says, okay, P2 is higher priority than P1, P2 is going to take over. Right. Looking at this timing diagram, who can see a disadvantage of this in comparison to cooperative multitasking? Yeah, so this is wasted time, basically. If you're not switching, then why did you give it to the operating system? And if you've got long, simple tasks or just one thing running at any point in time, you could actually waste a lot of your CPU doing this checking. However, generally speaking, it's an lot more powerful. Of course, another alternative is interrupts. So you are all pros on interrupts. Yes, you've done lab 4. So what we could do is we could just have, well, we're just going to have regular interrupts. And at every interrupt, we're going to say, okay, we're going to pick which process comes in next. And say you were to design this code with multiple interrupts and using your interrupt service routine to choose which process comes in, what would your code look like? Well, you would define your task basically in exactly the same way as in preemptive. And if you had interrupts, it could potentially look exactly the same in terms of flow of control. So, can anyone tell me what is the difference between preemptive multitasking and interrupt-based? Sorry? So the interrupt-based would bother with this wasted time because it would say, I'm having regular interrupts at this period and at this interval. Yeah, so the interrupts would be periodic. You'd have multiple interrupts, whole periodic processes, and so is there any difference at all between preemptive and just using interrupts? Nothing clear. The key is this interact service routine performs the context switch. So you'd have to write, say, you can imagine your interrupt, say, it might be count equals 2 to context switch. In other words, you would have to a priori plan all of your interrupts and when each process is going to take over. And whenever you're doing a context switch, you have to write the code within a context switch to take out your registers, store them to memory, load in the new registers. So knowing all this in advance is basically impossible unless you've got a very simple system. So you can do it with interrupts, but you're creating an awful lot more work than just using an operating system and assigning priorities. So those are our options, and should you wish, there's a nice brief PDF which you can look up on the website I showed you at the start, and it'll give you a nice introduction to these routines to have a look at yourself. And it's a very short read, and we recommend that you do it. Okay. Now, other problems with cooperative multitasking which I wanted to highlight is a potential long latency or poor responding to high priority events. Okay, so how does this occur? Imagine you've got some low priority process running, and in cooperative multiprocessing, it has the CPU. The high priority process wakes. Can it get the CPU? It has to wait potentially a very long time for this CS switch. And this very long time might be because of a programming error. You just wrote the wrong code. You forgot to type in CS switch. And so this can look and this is solved. So visually, if you wanted to imagine this task, you've got some low priority task running. You have an interrupt. becomes ready, but it can't run. This low priority task continues to run, and it's only here it switches because it says CS switch. And this idea that ISR making the task ready, this could be some external interrupt or a resource that the higher priority task was waiting for before it can continue. So essentially, what ideally you want to happen is after this interrupt service routine, the high priority task is ready to run. You want it to run immediately, but because there hasn't been a CS switch, it might not actually happen. And this is to highlight that in preemptive it will, and it all depends on the scheduling. The only other thing to point out on this slide is this UC Micro COS2. Micro COS2 is something that you all soon know and love because you're going to spend lots of hours working with this on the labs. So this is a real-time kernel that you'll be working with. It's very, it's well used. It's actually been used for on Mars rovers and stuff like that because it's particularly reliable. You could imagine if you have Windows running and crashing on Mars and someone needs to go press reset, it's not going to work so well. So you have, you need these real-time operating systems. The other interesting thing it has is a deterministic execution time. So this is a property that you'll only generally see on real-time operating systems. If you have, Windows, Linux, OS X, they won't be deterministic because they want to focus more on fair sharing, and they'll have other management tasks that run in the background. Whereas with a real-time kernel, you really want to know that things happen by a deadline. So that is the difference between real-time kernels and general operating systems. And yeah, so the example I talked about previously, if we have preemptive multitasking, the second the high priority task is ready, it runs. And then the low priority task can run once the high priority task is finished. And this is what's going to happen on Micro COS2. And we'll get lots of examples of that in future lectures. So a couple more things which we need to, it's just really terminology now. So an activation record is just your current copy of your process state, and the context switch involves the state of the current CPU and all of its registers, so that including the program counter, have to be stored into an activation record on memory. The context switch then says, I'm going to take a different process and I'm going to load that into registers and the program counter. So this is quite a simple task, but yeah, this is all that I've just said. So you copy the register across. The only complexity in context switching, note that you're moving registers from memory and you need to store these values, but at the same time be careful that, note that when you're moving it to memory, you're going to probably need some registers and you can't overwrite registers that you're trying to store. That's all this is trying to say. So in other words, you have to be careful. So how do you actually do context switching? Again, going back to ARM, it's actually a very simple idea. So this instruction here says store multiple increment after. So imagine I had a block of memory and I have some individual element in it. So what this says is R13 points to a location in memory. So store multiple increment after, what it says is saying store R0 here, then increments. store R1, then increment R2, R14. Move SPSR into R0 so that this is a special what is the current status of my program, so it has flags like errors, overflow, whether you're big endian, little endian, just general process information. And then you want to store this information as well, so it store multiple different before. So then you decrement R13 by 2, store R15 in here, and store R0 in here, which is actually the SPSR, and R15. So in other words, a context switch involves, this is my current state, I store this to RAM, or memory somehow, and extra variables to memory here. And so you can imagine the loading process is essentially exactly the same, but reverse. I've got my area of memory. I'm going to put R0, next proc into R0, R0 into R13. So R13 is going to point to a bit of memory. Then I'm going to load these two addresses to R0 and R14. This is going to go to my SPSR, and all of my other addresses are going to go back to R0, R1, R2, R13. So that's basically your idea of context switching. Store the current state to memory, load it back out. And this is the same example in NEOS so basically exactly the same idea. You have a stack pointer, which points to some location in memory. I'm decrementing 44 from it. Then I'm going to store R6, RA, frame pointer, R23 going up. Then I store R4, which is currently holding this is essentially saying the offset to memory from your current pointer and pointer location. Then it says load in the next address, OS task control block high ready. So load what the OS says is the high priority task, and take that from memory. You load all your registers into local registers. At the end of the context switch, we do this command ret, which does what anybody returns. It returns. How does it return? What's it returning from? So it's previous instruction of the new process. Yes? Which is stored in a register in NEOS. So yeah, at the end you do switch and continue running the new code. So that's an idea. Nothing you really need to know there apart from store all the registers safely, read all the registers of the new task. Right. A couple of terms. So threads are so-called lightweight processes that share memory space with other processes. So can anyone suggest why you would ever want a thread? Processes are similar. You have similar processes which share memory. Yeah, it might be useful. But then again, you have this problem of that you might have two processes overriding the same memory. right? So what you gain is a bit of speed. You actually have to do less context switching, right? You don't have to pull out all of your registers to memory. You can only pull out a handful. But the cost of that is that you could have one process overriding the other process. So you have to be a lot more careful. Now, in Linux, these are called pthreads, if you are interested. In microcs2, which you should be interested, they're called tasks. Now, you're going to spend all your lab writing tasks, which means you're not going to be writing processes, you're going to be writing threads. Why am I telling all this to you is whenever you write your tasks in microcs2, please give them a different memory space. It's very easy to make that mistake. You just copy a bit of code, or you copy your instantiation of a task, which looks something like this. If you don't name this stack or memory area as something different, you'll accidentally be writing over your data between processes, and that's going to muck you up like mad. So, and it's actually incredibly hard to debug why some process is suddenly having its memory change value. So that's just something to be aware of. The last bit that we'll mention today is this idea of reentrancy. So reentrancy is an ability of a program to concurrently execute different processes without mucking up. So I'll give you an example of a reentrant or a program that needs to be reentrant, and that is printf. So can anyone suggest why printf has to be reentrant? So suppose I have process 1, and it does something, and it calls printf. And it says hello. If I have process 2, and it does something, and it says printf, and it prints out David. If this program is not reentrant, what is it going to output? Will it print out hello David? Will it print out David hello? Yes? Who thinks it will print out hello David? Nobody. Who thinks it will print out David hello? Who thinks it will print out hello David O? One person thinks it's going to print out hello David O. The answer is it can print out any of them, right? Depending on which process got pulled out. Because they could execute concurrently, one could start writing it, the other could continue writing it. If it's not reentrant, then it could print out things in whatever order it happens. But if it's being reentrant, it's protected from this kind of behavior, so it will have to finish printing out whatever it has before it returns the CPU. Okay, I think this is best left for next week when we're going to talk more about code.